Welcome. This time I'm going to go through the viscous fluid equations and try and show you how viscosity affects the behaviour. And in particular I'm going to look at a quantity called the Reynolds number, which is a way of quantifying how important viscosity is compared to inertia effects, for example. And one major application of this is for numerical methods. Some viscosity is usually essential, and so I'll show you how Reynolds number plays a role in numerical methods and in choosing what viscosity is necessary or what grid resolution is necessary. So the equation we're going to look at is basically the momentum equation from the Euler equations with an extra couple of terms from viscosity. And so we have an equation for u, which is the flow velocity. We have the convective derivative again here. We have a pressure term. So rho here is the mass density, the gradient of pressure. Then we have the viscosity effects. So then we have a term which is, we have a mu over a rho, that's squared u, and we have 1/3. So we have a mu over rho. We have a divergence of u term here. And most of the time, this second term, if we assume that the fluid is incompressible or nearly incompressible, in this term's usually small. So the most important part is really this one, that we have essentially a second derivative of the velocity of the fluid flow, and this, if you take these terms together, so if I mark this term and this term, it essentially looks like a diffusion equation. So you have a d by dt, a time derivative on the left hand side and a second derivative of a quantity on the right hand side. And this is a diffusion of momentum, essentially a diffusion of the velocity, and has this mu as the viscosity coefficient. So this is the viscosity. Okay. Now what I want to do is essentially work out how important are these viscous terms, so how important is this term? And the important thing to work out is how important is it relative to this nonlinear term, so this inertia term here, which is essentially the advection of velocity by itself. So it's the flow of the fluid carrying momentum along, and then so this is the momentum being moved around by flow. And this is momentum moving because it's due to diffusion. So diffusion of velocity compared to advection of velocity. And this is where the Reynolds number comes in, because the Reynolds number is essentially the ratio of this advection term to this diffusion term. And so what we do is you work out approximately how large are these quantities. So approximate magnitude. And to do that, we need to pick typical values. So we essentially say that the gradients are of the order of 1 over a typical length scale. This is so L is a typical length scale. So it could be, for a fluid flow, it could be the typical width of the pipe, or size of the object that the fluid is flowing around. It could be a gradient scale length. So if you have a system, so a large system which has some gradients in its equilibrium quantities, then that might be a typical kind of large scale length scale. And u, obviously, we just write as a magnitude. So we just say that u has a magnitude which is roughly like a quantity u, and the same for the other quantities here. So we just say that there are some typical values we're going to pick, and so we just write that this first term, so u dot grad u, is of order basically u squared over L. And then the second term, the viscosity term, so we're going to write this as a write this down here, so we have mu over rho del squared u. That is of order mu over rho 1 over length squared times u. Now it's quite convenient to write mu over rho as a kinematic viscosity. So mu over rho we just define as nu, and this is the kinematic viscosity. Whereas this mu is the dynamic viscosity. Okay, so then this becomes nu u over L squared. Okay, so the Reynolds number is essentially how important this advection term is compared to the diffusion of velocity. And so it's the ratio of this first term to the second term. So to find Reynolds number, so RE, and this is just the ratio of this term to that term, so it's u squared over L divided by nu u over L squared. And this just becomes L u over nu. And so the larger the system, or the faster the typical velocities, the higher the Reynolds number, and the smaller the viscosity, again the higher the Reynolds number. And so when you have the combination of large systems, fast speeds and low velocities, this is where you get very large Reynolds numbers, and this is what typically causes problems for numerical methods, as we'll see shortly why. And essentially it's because we need the diffusion to control the dissipation, so that we need the solution to be smooth on the mesh scales, because we're using Taylor expansions or some smooth approximation. And so if you have a diffusion, we can make the solution smooth. And so on the mesh scales, we need this to be of order 1. And so if this is like the mesh spacing dx, we might need a very large number of mesh points to make dx small. If the velocity is large or the viscosity is small, then we need a very small dx. So we need a very small mesh spacing, so we need lots of grid points. So if Reynolds number is large, we might need a very large number of mesh points. And so for some systems, the Reynolds number becomes too large to solve exactly or accurately on a computer, and so you might have to make viscosity artificially large. So you might solve a system which has the same features, but with a viscosity which is 10 or 100 times larger than the real system, just in order to make this Reynolds number roughly 1 on the grid scale. If Reynolds number is much larger than 1, then viscosity is not important. And conversely, if Reynolds number is much smaller than 1, then there's only viscosity. And the interesting regime, so where we have Reynolds number is roughly 1, so here we have viscosity balances the advection terms. And at this point, the viscosity can provide a smooth solution, or can smooth the solution, and make it much easier for numerical methods to approximate the solution. So we need a smooth solution on the mesh, because we're using Taylor expansions. So we're assuming that the solution is smooth, we can use polynomials and just smoothly go between the grid points, and so therefore, so we need a diffusion. We need some kind of diffusion to ensure we have a smooth solution. And typically this means we need Reynolds number around 1 on the mesh. So when L is roughly delta x, so the grid spacing. And so we need that delta x times u over over the viscosity should be roughly 1. And so delta x is roughly nu over u. So if you have very small viscosity or a very large velocity or speed, then you need a very small grid spacing to be able to get this smooth solutions. So I'll show you what effect this has if you go to a Jupyter notebook. So this is essentially the same example I showed in a previous lecture where we looked at waves in a one-dimensional system. I've just modified it a little bit and added the viscosity terms. So we're using SciPy's ODE int to do the time integration. We're using first and second derivatives now. So we have a second derivative term for the viscosity, first derivative term for all the other derivatives. So we have a central differencing for both. If you're not sure where these came from, look at a previous video where I derived them. So here we define the functions. So here using a NumPy roll which shifts all the values one point to the left or to the right. And so this first equation here, this is this first derivative up here. So roll with a -1 is xn plus 1, and roll with a +1 is fn minus 1. And so this is the first derivative, and this term here, you can see by comparing it to this is the second derivative term. And so now we have this system of equations we're solving. So it's in one dimension, and so the whole set of equations just reduces to this. So we have the velocity equation, so a pressure term, and then the viscosity terms. The two viscosity terms just collapse into one term here, with now a 4/3 factor, and we have a pressure equation here. And as before, we expect the sound speed roughly this. So most of this is the same as before. So we have a length of the system of 1. Now I've got 100 grid points, and so we have the length is just an array of 100 grid points. It goes from 0 to 1, 0 to the length. We define a constant density, so we're not evolving the density here, and we have a mu, a gamma, which is the ratio of specific heats here, and we have a mu, which is the viscosity. And for now I'm keeping the viscosity 0, just to show you what happens. Okay, so then we have a function we define which solves the set of equations. So f here is the array of all the values being solved. So we have 100 grid points, 100 mesh points, so we have 200 values we're solving. So this consists of 100 values of the velocity, followed by 100 values of the pressure. And so that's what this is doing. This is taking the first n, so the first 100 values, and putting in ux, and the second 100 values and putting in pressure, in P. And then these are the equations we're actually solving. So here we have the advection term, so ux times dux by dx. You have the pressure term, so it's just a derivative dp by dx. And this is the second derivative, which is another function we defined above, which is the second derivative of ux. And then the pressure equation, again, the advection term and the compression term. So d by dx of ux. And then these just define arrays, so if you have 100 grid points, these are each 100 long. And then we join them together, we concatenate them, so that the array we send back, we return, is an array of 200 values. So the same as f went in. And so the order is ux first and then p second, the same as what came in, so ux and then p. So then the initial conditions, so in a previous talk I looked at a case where we had a zero velocity and a small perturbation in pressure. Now we have a case where I have a constant pressure, so this is 3/5 just to make the sound speed equal to 1, and we have a sinusoidal variation in velocity. So ux here is the velocity, so it's positive and then negative, so it's just a sine wave. So now we can try and do this. Okay, so now we have a Reynolds number, obviously, which is infinite because we have a 0 here, so mu is 0, so we've blown up that expression. But we can still solve the equation, so we can integrate it. So these are the times we want the values, so it starts at 0, t equals 0. Because the sound speed is equal to 1 and the length of the box is equal to 1, we expect an oscillation which has a period of 1, and so this final time here is after exactly one period of the oscillation, and so the final time should look a lot like the first. Okay, so then we integrate in time using ODE int from SciPy. This is the function which calculates the time derivatives above. We give the initial conditions joined together in one array, and these are the times we want the output. So it runs through, but it produces this warning. So excess work done on this call. So it's taking too many steps typically. So usually this is a warning sign that something has gone wrong with the calculation. And then this is the plot. So this again is looping over each value of the output times, taking the result at that particular time index, and then extracting the velocities and the pressures, and here it's plotting the velocity. And so what you expect is a sine wave, but what we get is essentially this. So we end up with a large oscillations and essentially an unstable solution. So it's quite easy to break this system, so unless we have some kind of dissipation. So typically this is a sign that you need some kind of dissipation in the system to control these oscillations. And we argued previously that we need a Reynolds number of about 1 on the mesh spacing. So this has been calculated using the maximum velocity, the mesh spacing, and mu here. And this is not 1, it's infinite in this case. So we need some kind of dissipation. So I'll set this to 0.1, for example. What we get. So now I have Reynolds number of 0.1, so it's a very small, well, smaller than 1. Now I can plot this, and this is what I get. So now I have a nice smooth solution. So this is the initial conditions are this curve here. And you can see it rapidly damps, so that by the time you get to this curve is the final time. You can see it's oscillating, but it's also decaying, it's damping very quickly. And this is the dissipation, see, from the viscosity. So we can afford to turn this up a bit. So if this is 0.1 here, we can make mu about 10 times smaller and make Reynolds number on the grid scale about 1. And so we can do this here. So let's make this 0.01. And so now Reynolds number on the grid scale is 1. And again, we can integrate this. And so now you get a system which it's evolving. It's no longer damping after the initial transients. So it's very slowly damping, but much slower than before. And you see you now have these steep gradients which are propagating around the system. So these are essentially this system, this wave here. This gets steeper and steeper. This gets steeper and steeper here. So it makes a kind of S-shaped kind of curve here, and then this propagates around through the system, and you can get these steep gradients here. And these are what's causing the problems before. These sudden jumps in the velocity.